Okay, so we spent the last lesson looking at evaluating limits graphically. And today's lesson, we're going to look at evaluating limits analytically. Okay, so evaluating limits analytically, you want to think of it as like evaluating limits algebraically. That's fine as well. So we're going to jump into just doing some examples with this, and we'll talk about like the techniques we're going to utilize to evaluate limits analytically or algebraically. Okay, so with the first limit, we're taking the limit as x approaches 1 of 2x plus 7. Okay, so first thing we always want to check whenever we evaluate limits analytically or algebraically is, can we use direct substitution with our limit and get a valid output? And when we look with example number 1, if we directly substitute 1 in the place of x, that's going to give us a valid output. That's going to give us 2 times 1 plus 7, which is going to be 2 plus 7, which is equal to 9. Okay, so not only do I want us to be able to evaluate a limit analytically or algebraically, but I also want us to understand what that limit tells us about the graph of our function. And if we're able to use direct substitution right off the bat and get a valid output, then that tells us that our graph contains the input value, which in this case is 1, and then when we input 1 into that function, it gives us an output of 9. So that graph is going to contain the ordered pair 1, 9. Okay, when we look at number 2, again, we're taking the limit as x approaches negative 2 of x minus 1 over 3x plus 4. Okay, so again, we want to try to use direct substitution and see if we get a valid output here. So when we input negative 2 in the place of x, the numerator is going to be negative 2 minus 1. And then our denominator is going to be 3 times negative 2, which is going to be negative 6 plus 4. And that numerator is going to simplify to negative 3. The denominator is negative 2. So negative divided by a negative is going to make that quotient positive. That winds up becoming 3 halves. So since we were able to use direct substitution and get a valid output, that means that the graph contains or passes through the point negative 2 comma 3 halves. Okay, so again, when we evaluate limits analytically or algebraically, like when in cases where you're able to use direct substitution like this, they're the easiest limits to evaluate. Unfortunately, the majority of limits that you guys are going to run into, that's not going to be the case. Okay, you're not going to be able to use direct substitution immediately right off the bat and get a valid output. So we'll take a look at what happens when we can't use direct substitution right off the bat with the next several examples we're going to look at. So when we look at number 3, we are taking the limit as x approaches 1 of x squared minus 1 over 1 minus x. Now, if we try using direct substitution for this limit, we get the numerator to be 1 minus 1, which is 0. It should be 1 minus 1, which is equal to 0. And the denominator is going to be 1 minus 1 as well, which is equal to 0. So we get something of the form 0 over 0, which is not a valid output for us. Okay, but this is going to be a circumstance that you run into a lot when evaluating limits analytically or algebraically. Okay, so when this is the case where we can't use direct substitution, there is usually one of 3 techniques that we can use to evaluate limits of this type. Okay, so the first technique that we're going to use is to factor the numerator and the denominator. And then we want to see if there is a common factor that we can eliminate. Okay, so we typically want to try that first. The second technique that we can use if that first technique does not work is we can multiply the numerator and denominator by the conjugate. Okay, so hopefully you know what a conjugate is. If not, we'll talk about what a conjugate is when we get into examples where we have to utilize that technique. Okay, and then the third technique is to simplify the numerator and denominator. Okay, and typically using one of these three techniques, we'll be able to manipulate our numerator and denominator where we will eventually be able to use direct substitution. Okay, so again, you always want to try to use direct substitution first. If that gets you a valid output, great. If it gives you something of the form 0 over 0, that's good news for you as well, because one of the three techniques that I just described, you can use to evaluate that particular limit. So when I look at number 3, I think the best candidate for number 3 is to factor both the numerator and denominator. Okay, now when you guys are working out limits, you have to, okay, this is a must. You have to write your limit every single step until you actually plug that number into your function. Okay, so again, we have to write the limit as x approaches 1 every single step until we actually plug that number into our function. Okay, so I'm going to attempt technique number 1 here, factoring the numerator and denominator. So when I look at that numerator, that's going to be the difference of two squares. So I know that that numerator is going to factor to x plus 1 times x minus 1. Now, the denominator 1 minus x looks very similar to x minus 1, but those two factors aren't the same. Okay, they're what are called additive inverses, because if I add 1 minus x to x minus 1, those are going to add up to 0. Okay, so when you have factors that are additive inverses, what you can do is you can factor a -1 out of one of the expressions. So if I factor a -1 out in the denominator, that is going to give me the resulting factor in the numerator, because the opposite of x minus 1 is 1 minus x in that denominator. Okay, so once we're able to eliminate that factor, that was the factor that made both the numerator and denominator 0. Because when I plug 1 into both of those factors, that makes the numerator and denominator 0. So once I get rid of that factor, I should now be able to use direct substitution to evaluate that limit. Okay, so this is going to become the limit as x approaches 1. I'm going to take that factor of -1 in the denominator and apply it to the numerator. Okay, so that's like saying the opposite of x plus 1. And now I can use direct substitution. Okay, so when I plug 1 in the place of x, this gives me the opposite of -1 plus 1, which is -2. Okay, now let's take what we know about rational functions to figure out what this limit tells us about the graph of our function. Okay, so when we look at that rational function, we see that that rational function is not in lowest terms because we were able to cancel the factor of x minus 1 in the numerator and in the denominator. So if you guys remember, like when we looked at rational functions, if they weren't in lowest terms, if you could cancel a factor in the numerator and denominator, that tells you that your graph has a hole. So the x coordinate that makes that canceled factor 0 is 1. And that's where we're taking our limit at. So there's going to be a hole at the point 1. And then when we plug 1 into the simplified function, which is what we did down here in that highlighted step, when we plug 1 into the simplified function, the output is going to be the y-coordinate of our hole. Okay, so this limit here tells us that our graph has a hole at the point 1, -2. And that's going to be really important for you. Okay, anytime you try using direct substitution and you get your limit to be of the form 0 over 0, that tells you that your graph is going to have a hole. Okay, so this is how we will see like holes represented in limit form. Okay, let's take a look at number 4. So for number 4, we have the limit as x approaches 2 of x cubed minus 8 over x squared minus 4. All right, so again, we want to use a direct substitution first to see if it gives us a valid output. Well, when we try plugging 2 into both the numerator and the denominator, 2 cubed is 8, minus 8 makes the numerator 0, and then 2 squared is 4, minus 4 makes the denominator 0 as well. So again, we get something of the form 0 over 0, which is not a valid output for us, but since when I try using direct substitution, we get something of the form 0 over 0, that tells me that my graph is going to have a hole. Okay, so again, I can use one of the 3 techniques that we talked about up here, either factoring, multiplying the numerator and denominator by a conjugate, or simplifying the numerator and denominator. I can use those to evaluate this limit in particular. Okay, so for me, this is going to be a candidate for factoring. And when I look at that numerator is of the form x cubed minus 2 cubed, which is the difference of 2 cubes. All right, so I don't know if you guys remember this from last year, but I'm going to review it really quick. I want to review factoring the sum of 2 cubes and the difference of 2 cubes, because the process that we use to factor each is going to be the same. Okay, now the acronym that we use to factor the sum and difference of cubes is going to be SOAP. Okay, so you're going to want to remember that acronym when factoring the sum and difference of cubes. And what that acronym SOAP tells you is it's going to tell you the signs in your factors when you factor the sum and difference of cubes. So the S in SOAP stands for same. The O in SOAP is opposite. A is for always. And P is for positive. Okay, so the process that we use for factoring the sum and difference of cubes using SOAP is exactly the same. So for both of these, your first factor is going to be a binomial factor. And the second factor is a trinomial factor. Okay, so when we use our acronym for SOAP, the first sign, so the sign in the binomial factor, is going to be the same. So for the sum of 2 cubes, that first sign is going to be plus. For the difference of 2 cubes, that sign is going to be minus. Okay, the next sign is going to be opposite. So for the sum of 2 cubes, the sign is plus. When we take the opposite, that's minus. For the difference of 2 cubes, the sign is minus. The opposite is going to be plus. And then the last sign is always positive. Okay, so all we have to do to get our terms in our binomial and trinomial, our first term is going to be the value of that first factor. So we're taking a and raising it to the third power. So that first term is going to be a. The second term is going to be b. And then for the trinomial, the first term is going to be a squared. The middle term is going to be a times b. And the last term is going to be b squared. Okay, so again, the sum and difference of cubes factor using the same process. We are just using the acronym to give us our signs. Okay, so again, when we try using direct substitution for 4, we get something of the form 0 over 0. So we're going to use one of the 3 techniques, again, that I mentioned up here. We're going to use factoring here. So when I factor the difference of 2 cubes in the numerator, that's going to factor to x minus 2 times x squared plus 2x plus 4. Again, that's a minus b times a squared plus ab plus b squared. And then that denominator is the difference of 2 squares, so that is going to factor to x minus 2 times x plus 2. And again, we see that that rational function is not in lowest terms because we're able to cancel that factor of x minus 2 in the numerator and denominator. And then once we cancel that factor, that was the factor that made both the numerator and denominator 0. So once we eliminate that factor, now we should be able to use direct substitution and get a valid output. So when I directly substitute 2 in the place of x, we get 2 squared, which is 4, plus 2 times 2, which is 4, plus 4, over 2 plus 2, which is 4. So that becomes 12 divided by 4, which makes that limit there 3. Okay, so not only do we want to be able to find that limit, but we also want to determine what that limit tells us about the graph of the function. So that limit tells us that our graph has a hole at the point 2, 3. Because again, 2 is the value that makes the canceled factor 0. Okay, so that's the x coordinate of the hole. And then when we plug 2 into the simplified function, like we did evaluating the limit, that's going to give us the y coordinate of the hole. Okay, I want you guys to try number 5. So for 5, you have the limit as z approaches 9 of 9 minus z over 3 minus rad z. All right, so pause the video while you attempt that one. Okay, so with 5, we have the limit as z approaches 9 of 9 minus z over 3 minus rad z. Again, we want to try to use direct substitution first. But when we try direct substitution, the numerator becomes 9 minus 9, which is 0. The denominator is 3 minus rad 9, which is 3 minus 3, which is 0 as well. Okay, so we don't get a valid output with direct substitution. But because this is of the form 0 over 0, I'm going to be able to manipulate this in some way where I will eventually be able to find the limit. Okay, now when I look at the 3 techniques that I can use here, I think at first glance, and if I were to guess, I would guess very few, if any of you, tried to factor this. It actually is factorable. We'll take a look at that in a second, okay? But I'm going to guess that most of you guys, when attempting to do this, probably try to multiply the numerator and denominator by the conjugate of the denominator. Okay, so that's technique number 2, the conjugate. Okay, so the conjugate of the denominator, we're keeping the 2 terms the same, 3 and rad z, and then we're going to change the signs in between them. Now, you guys should be very familiar with this because if you multiply a plus b times a minus b, a plus b and a minus b are conjugates. The 2 terms are the same. They're separated by a different sign. And when we multiply out a plus b times a minus b, that gives us a squared minus b squared. Okay, so when I look at multiplying across in the numerator and in the denominator, when I multiply the numerator, I'm going to keep that numerator in factored form. And the reason being is I want to cancel that with a factor in my denominator. And when I multiply in my denominator 3 minus rad z times 3 plus rad z, again, that's of the form a minus b times a plus b. That's going to give me a squared minus b squared. Okay, so a squared, that's 3 squared, which is 9, minus rad z squared, that's going to become z. And again, we see that our rational function here is not in lowest terms because we can cancel that factor of 9 minus z. So once we get rid of that factor, that's the factor that make both the numerator and denominator 0. We can go ahead and now use direct substitution to evaluate that limit. So when we plug 9 in the place of z, we get 3 plus 3, which makes that limit there equal to 6. Again, not only do I want you to be able to figure out what that limit is, but also what that limit tells you graphically. And that limit tells us graphically that there's a hole at the point 9, 6. Okay, but as I mentioned before, that's not the only way to do this problem. Believe it or not, you guys can actually factor this as well. Because when you look at that numerator 9 minus z, you can write that as the difference of two squares. It is 3 squared minus rad z squared. So again, that's like of the form a squared minus b squared, that's going to factor to a plus b times a minus b. Okay, so you can actually take the limit as z approaches 9. That numerator is going to factor to 3 plus rad z times 3 minus rad z. And that denominator is 3 minus rad z. So you can eliminate that common factor and now use direct substitution in the numerator, which is going to be 3 plus rad 9, which is 3, which makes that limit equal to 6. Okay, so again, because you were able to cancel a common factor, that rational function was not in lowest terms. So again, this limit tells us that there is a hole at the point 9, 6. And again, either of those two techniques is fine. If you want to multiply the numerator and denominator by the conjugate of the denominator, that's perfectly okay. If you want to factor the numerator and then cancel the common factors in the numerator and denominator, that's okay as well. I'm just showing you two different techniques that you can use for this problem. Okay, so we'll stop this video here. We'll pick up with the next example in the second video.